sklearnutils. Description: explain in detail. The scikit-learn sklearn library in Python provides a collection of utility functions, commonly referred to as utils, that offer valuable tools for data preprocessing, model evaluation, and general machine learning tasks. These utilities streamline common operations and enhance the overall efficiency of machine learning workflows. Inputs. Input 1. Explain in detail. The primary input to sklearnutils is typically a dataset, often represented as a NumPy array or a pandas data frame. This dataset contains the features independent variables and potentially the target variable. Dependent variable for machine learning tasks. Input 2. Explain in detail. Depending on the specific utility function, additional inputs might be required, such as model parameters for model evaluation utilities, parameters like the model itself, the predicted labels, and the true labels might be needed. Preprocessing parameters for data preprocessing utilities. Parameters like the desired scaling method or the specific feature transformations might be specified. Outputs. Output 1. Explain in detail. The outputs of sklearnutils vary depending on the function. Common outputs include processed data. Data preprocessing utilities might return the transformed dataset after applying scaling, encoding, or other operations. Model evaluation metrics. Evaluation utilities generate metrics such as accuracy, precision, recall, F1 score, and other relevant measures for assessing model performance. Feature importance. Feature selection utilities can output the importance scores or rankings of features, helping identify the most influential variables. Steps. Step 1. Explain in detail. The steps involved in using sklearnutils typically follow a general pattern. Import the necessary utilities from sklearn. Prepare your dataset. Load, clean, and format it appropriately. Instantiate the desired utility function with any necessary parameters. Apply the utility function to the input dataset or other relevant data. Interpret and utilize the outputs generated by the utility function. Metrics. Metric 1. Explain in detail. Sklearnutils themselves don't directly define metrics. Instead, they provide tools to compute and evaluate metrics. Some common metrics used in conjunction with sklearnutils include accuracy, the proportion of correctly classified instances; precision, the proportion of true positives among predicted positives; recall, the proportion of true positives among all actual positives; F1 score, the harmonic mean of precision and recall; mean squared error. MSE measures the average squared difference between predicted and actual values. Visualization plots. Visualization plot 1. Explain in detail. Sklearnutils don't inherently generate visualizations. However, many of their outputs can be used to create insightful plots using libraries like matplotlib or seaborn. Examples include confusion matrix visualizes the performance of a classification model by showing the counts of true positives, true negatives, false positives, and false negatives. ROC curve plots the true positive rate against the false positive rate for different classification thresholds. Precision recall curve visualizes the trade-off between precision and recall for different thresholds. Feature importance plot shows the ranking or scores of features based on their importance in a model. Fine-tune parameters. Parameter 1. Explain in detail. Depending on the specific sklearn utility function, there might be parameters that allow for fine-tuning its behavior. For instance, a scaling utility might have parameters to control the scaling method, e.g., standardization, normalization, And feature selection utilities might have parameters to adjust the selection threshold. Uncertainty methods. Uncertainty method 1. Explain in detail. sklearnutils don't natively provide uncertainty quantification methods. However, they often serve as building blocks for uncertainty estimation techniques. For example, cross-validation methods, e.g., k-fold cross-validation provided by sklearn can be used to generate multiple model predictions and estimate uncertainty by analyzing the variability in these predictions. Challenges and fixes. Challenge 1. Explain in detail data inconsistency. Inconsistent data formats, missing values, or unusual data distributions can lead to issues with data preprocessing and model training. Sample use case that resulted in Challenge 1. A dataset with missing values in some features, causing problems with certain scaling methods that assume complete data. Fixes to Challenge 1. Impute missing values. Use techniques like mean imputation, median imputation, or more advanced methods like KNN imputation to replace missing data. Handle categorical features. Encode categorical variables appropriately using methods like one-hot encoding or label encoding. Normalize or standardize data. Apply scaling methods like standardization or normalization to address differences in data ranges and scales. Challenge 2. Explain in detail incorrect data transformations. Applying inappropriate data preprocessing techniques or transformations can negatively impact model performance. Sample use case that resulted in Challenge 2. Scaling features using standardization when normalization would be more suitable for the specific data distribution. Fixes to Challenge 2. Analyze data distribution carefully. Examine the distribution of features to determine the most suitable scaling or transformation method. Experiment with different methods. Try different preprocessing techniques and evaluate their impact on model performance. Use domain expertise. Consult domain experts to understand potential data characteristics that might necessitate specific preprocessing steps. Challenge 3. Explain in detail overfitting or underfitting. Improperly tuned parameters or data preprocessing can lead to overfitting. High performance on training data but poor generalization, or underfitting. Poor performance on both training and test data. Sample use case that resulted in Challenge 3. Using too many features in a model without proper feature selection can result in overfitting. Fixes to Challenge 3. Regularization. Apply techniques like L1 or L2 regularization to penalize complex models and prevent overfitting. Cross-validation. Employ cross-validation techniques to evaluate model performance on unseen data and avoid overfitting. Feature selection. Select relevant features using methods like feature importance ranking or dimensionality reduction techniques. Challenge 4. Explain in detail incorrect metric selection. Choosing an inappropriate evaluation metric can misrepresent model performance. Sample use case that resulted in Challenge 4. Using accuracy as the primary metric for imbalanced datasets might be misleading, as it favors models that predict the majority class well. Fixes to Challenge 4. Understand the task. Clearly define the goals of your machine learning task to select the most relevant metrics. Use multiple metrics. Consider evaluating model performance using a combination of metrics to get a more comprehensive picture. Analyze the data. Examine the characteristics of the data, e.g., class imbalance, multicollinearity, to choose metrics that address potential biases. Challenge 5. Explain in detail poor model choice. Selecting an inappropriate model for the task or data can lead to suboptimal performance. Sample use case that resulted in Challenge 5. Using a linear regression model for a highly nonlinear dataset. Fixes to Challenge 5. Analyze data patterns. Explore the relationships between features and the target variable to choose a model that fits the data patterns. Experiment with different models. Try different model types, e.g., linear, tree-based, neural networks, and compare their performance. Consider domain knowledge. Involve domain experts to identify appropriate model types for a specific application. Challenge 6. Explain in detail computational resource constraints. Some pre-processing techniques or models might be computationally expensive, requiring significant resources. Sample use case that resulted in Challenge 6. Training a deep neural network on a large dataset might require extensive processing power. Fixes to Challenge 6. Optimize algorithms. Select efficient algorithms or use optimized libraries for computationally intensive tasks. Reduce data size. Consider techniques like data sampling or dimensionality reduction to reduce the computational load. Utilize cloud computing. Leverage cloud platforms with powerful computing resources to handle large datasets and complex models. Challenge 7. Explain in detail limited interpretability. Some machine learning models, particularly complex ones, can be difficult to interpret. Sample use case that resulted in Challenge 7. A black box model like a deep neural network might provide accurate predictions but lack insights into the decision-making process. Fixes to Challenge 7. Use interpretable models. Choose models known for their interpretability, such as linear models or decision trees. Feature importance analysis. Investigate feature importance scores to identify the most influential variables in the model. Explainability techniques. Explore explainability techniques like sharp values or LIME to provide insights into model predictions. Challenge 8. Explain in detail data leakage. Introducing information from the test set into the training data can lead to artificially inflated performance. Sample use case that resulted in Challenge 8. Using features from the test set during data preprocessing or model training. Fixes to Challenge 8. Ensure data separation. Keep training and test data strictly separate throughout the entire process. Perform data preprocessing independently. Apply preprocessing steps only to the training data and use the same steps without refitting to transform the test data. Avoid using information from the test set. Ensure that no information from the test set is used during model training or evaluation. Challenge 9. Explain in detail incorrect hyperparameter tuning. Using inappropriate hyperparameter values can significantly impact model performance. Sample use case that resulted in Challenge 9. Setting a learning rate that is too high or too low in a gradient descent algorithm. Fixes to Challenge 9. Grid search. Experiment with a range of hyperparameter values using grid search or random search techniques. Cross-validation. Use cross-validation to evaluate model performance with different hyperparameter settings. Early stopping. Monitor model performance during training and stop training when performance on a validation set starts to plateau. Challenge 10. Explain in detail lack of robustness. Models can be sensitive to small changes in the input data, leading to unpredictable behavior. Sample use case that resulted in Challenge 10. A model trained on a specific dataset might perform poorly on data with slightly different characteristics. Fixes to Challenge 10. Robust preprocessing. Employ preprocessing techniques that are robust to outliers or noisy data. Ensemble methods. Use ensemble methods like bagging or boosting to combine predictions from multiple models, reducing the impact of individual model errors. Data augmentation. Generate synthetic data variations to improve model robustness and generalization. Challenge 11. Explain in detail bias in data. Data can reflect existing biases present in the real world. leading to models that make unfair or discriminatory predictions. Sample use case that resulted in Challenge 11. A model trained on a biased dataset might perpetuate racial or gender disparities. Fixes to Challenge 11. Collect diverse data and ensure that the training data represents the diversity of the population or system you are modeling. Bias detection and mitigation. Use techniques to identify and mitigate bias in the data and model. Fairness metrics. Evaluate model performance using fairness metrics that assess the impact of a model on different groups.